Okay, so in the previous lecture, we had discussed the fact that if I consider a finite dimensional complex inner product space, then I can talk about it be a linear operator on it being normal if and only if it consists of an orthonormal basis of eigenvectors. So a quick recall that if V is a finite dimensional complex inner product space, then a linear operator defined on V is normal, normal if and only if it has an orthonormal basis, consisting of eigenvectors, if you recall, right? Consisting of eigenvectors. So what we try to do in this lecture is that we want to prove an analogous statement for real real finite dimensional inner product spaces. Okay, so how can we do that? Now, when we had studied the rotational operator, we had seen that the matrix related to the rotational operator in terms of the standard basis, it was normal, but it had no eigenvector, right? So another recall is that if I consider T from R2 to R2 to be the rotational operator which rotates via an angle theta between 0 to pi, then we had the matrix of T with respect to the matrix of T with respect to the standard ordered basis of R2 to be of this form, right? It was of the form cos theta minus sin theta cos theta, right? Now there, what I just said is that there we had seen that it has it is normal, but it has no eigenvector. And it also immediately follows from the fact that when we are rotating a vector, it's no more scaled, right? We had discussed these things in the previous lecture. So we require some additional tool in order to talk about the diagonalization inside a real inner product space in terms of orthonormal basis. Okay, so how can we do that? To do that, the tool we require is what we call a self-adjoint operator. Okay, what we call a self-adjoint operator. Okay, so the definition is pretty obvious and simple as well. Let T be a linear operator where V is some inner product space, then we say that T is self-adjoint, or we say that T is Hermitian, if T equals its adjoint. Okay, if T equals its adjoint. So in a way, if I talk about the matrix analog of this definition, then I guess you people have already understood why I use the term Hermitian. An n cross n matrix is said to be, one second guys, okay, so an n cross n matrix is said to be Hermitian, and here we stick to the term Hermitian if it equals its conjugate. Okay, Now, here we are not talking about the inner product space being a real inner product space or a complex inner product space. Obviously enough, if V is a real inner product space, then clearly talking about its conjugate is same as talking about its transpose, right? So this definition in terms of a real inner product space is simply talking about symmetric matrices, right? Now, what I just said previously is that though in complex finite dimensional inner product spaces, being normal is equivalent to speaking about the existence of an orthonormal basis of eigenvectors, it's not at all justified in case of a real inner product space, and the example is the rotational operator. And for that, to ensure that existence, what we require is a further restriction to the operator. It needs to be normal, but the restriction we need above being normal is it being self-adjoint. Now it's quite evident that if it's a self-adjoint operator, then it's indeed normal, right? So I guess this is a much weaker statement in the case that, you know, being normal is weaker to stating it's self-adjoint in some sense, right? Like all through whatever analysis we have studied, we've always seen that the complex analysis is sort of more rigorous than real analysis, right? Complex numbers typically are algebraically closed, and that actually affects everything, and it sort of generalizes concepts which could not have been possible in case of real analysis, right? So the same thing obviously carries over from the fact that the complex field is algebraically closed. The main thing which I actually want to refer to is that why can't we say about the existence of eigenvectors in terms of real inner product spaces is that we cannot guarantee that the characteristic polynomial of the operator will split whenever I am talking about a real inner product space. While we know that the characteristic polynomial will obviously split in a complex inner product space due to the fundamental theorem of algebra, and that's why we need some extra restriction to the operator so that we can ensure the fact that the characteristic polynomial of the operator we are talking about surely splits, right? And that is what will be our lemma. So the lemma says that for self-adjoint operators, the eigen values are all real. Okay. The lemma is that let T be a self-adjoint operator. Let T be a self-adjoint operator on a finite dimensional inner product space V. Then number one, all eigenvalues are real. So in a way, this also proves the fact that if I talk about symmetric matrices, symmetric real matrices, then all the eigenvalues must be real. Number two is that suppose V is a real inner product space. V is a real inner product space, then the characteristic polynomial splits. Okay, splits into linear factors, you might say also. Okay. Though, sorry, I shouldn't use the term linear factors. Power of linear factors should be the more precise statement, right? Okay, let's prove this out. The proof is fairly simple. Proof. See, suppose I talk about an arbitrary eigenvalue. Let lambda be an eigenvalue of T. Then by definition that there exists some non-zero vector x in V such that Tx is equals to lambda x. Now, we also know that a self-adjoint operator is a normal operator as well, right? That directly follows from definition. So if it's normal, then I can say that T star of x must be lambda bar x. This was covered in the previous lecture, right? But then T star of x is nothing but Tx. So now T star of x is nothing but Tx because T is equals to T star for T being given to be self-adjoint. But then Tx is equals to lambda x. And this happens. So that implies that lambda x is equals to lambda bar x. But that obviously implies that lambda is equals to lambda bar since x is non-zero, right? But then what sort of complex numbers are such that their conjugates are equal to them, right? This obviously implies that lambda is real, right? So this is a very, very easy proof. The next proof is also quite simple, because let dimension of V be n, and let beta be an arbitrary orthonormal basis, for V. Okay. Now we are to show that T, the characteristic polynomial of T, splits over R. That's whatever actually we need to show, right? And what I can actually do is that firstly I don't need to restrict the field to the reals. I can restrict the field to the two complexes only, but I can actually show that the characteristic polynomial, which will surely split in C, it will be actually also splitting in R, right? That is, it will be of the form, say, T minus lambda. Each component will be of the form T minus lambda, where lambda is real. That's exactly what I need to show, and I can in fact do it. Why can I do it? Because since I am talking about a self-adjoint operator, the eigenvalues will surely be real, right? And the characteristic polynomial simply gives the eigenvalues as roots. So I guess there is some overview of this proof. So let beta be an orthonormal basis for V, and let A to be the matrix of T with respect to beta. Okay. Now consider the linear operator, say TA is equals to AX. Okay. Then TA is self-adjoint, right? TA is self-adjoint. Why is it so? Because this is fairly obvious that the matrix of TA with respect to gamma is just A, where gamma is the standard ordered basis, over Fn, right? Sorry, gamma is the standard ordered basis. Yeah, I am talking about TA. Yeah, okay. Gamma is the standard ordered basis over Fn, correct? Right? Because dimension of E is taken to be n, it's quite obvious. Okay. Now, since TA is self-adjoint, what more can I say? So this implies that every eigenvalue of TA is real, right? Of TA is real. But this implies that the characteristic polynomial of TA splits, and it splits into factors of the form T minus lambda, as I was speaking, such that these lambdas are real, right? So that implies the characteristic polynomial of TA splits over R, because the roots we will be getting are all real. But then the characteristic polynomial of TA is same as the characteristic polynomial of A, and it's same as the characteristic polynomial of T, because changing the basis doesn't cause a difference in the characteristic polynomial, right? And hence the characteristic polynomial of T, hence the characteristic polynomial of T splits, because the characteristic polynomial of TA splits, right? So it's a very simple proof. And now we come to the theorem which I wanted to prove, is that if I consider a self-adjoint operator, then I can say that I can equivalently talk about the existence of an orthonormal basis of vectors. Okay, let T be a linear operator on V, where V is a real finite dimensional inner product space. Then T is self-adjoint if and only if there exists an orthonormal basis. There exists an orthonormal basis beta for V, such that, or let me just say, consisting of the eigenvectors of T. Okay, and the proof is fairly simple. Why is it simple? We just do it in this way. What can we actually do is that, see, suppose let's say suppose T is self-adjoint, then okay, we can do it in this way, that if T is self-adjoint, then there exists an orthonormal basis such that the characteristic polynomial splits to give the matrix of T with respect to beta, which is the orthonormal basis, is upper triangular, right? So suppose T is self-adjoint, then uh, then there exists an orthonormal basis. Then there exists an orthonormal basis beta for V such that A, which is the matrix of T with respect to beta, is upper triangular, right? Is upper triangular. But A star is equals to A as T star is equals to T, right? Right. But then A star is equals to A, where A is upper triangular. Since A is upper triangular and A star, which is actually simply A transpose, because we are talking about real inner product spaces, is equals to A, this simply implies that A is diagonal, right? I guess this part is clear. Okay. Okay. Clear. And the converse is trivially true, right? Because in the previous lecture we had seen that by Schur's theorem, that if T is a linear operator over a finite dimension inner product space, and suppose that the characteristic polynomial of T splits, then there exists an orthonormal basis such that the matrix of T with respect to that orthonormal basis is upper triangular. Now, since we are talking about real inner product spaces, we have already seen that the characteristic polynomial of the self-adjoint operator will split, right? So the converse is trivial. I mean, so this part is trivial. That is, this existence of orthonormal basis is trivial. Converse part, there is nothing to prove, right? Because if there exists an orthonormal basis for V which consists of eigenvectors, then the matrix of T with respect to that orthonormal basis is already diagonal. If it's diagonal, then the transpose of A will equal A, or in other words, the adjoint of A will equal A, right? A star will equal A. But if A star equal A, then T star will also equal T. Right? So that's the trivial case. Yeah. So yeah, that's good. Now see, um, real symmetric matrices. This is just a simple observation. See, real symmetric matrices are self-adjoint. Real symmetric matrices are self-adjoint. So that implies that the self-adjoint implies normality, right? Clear? Should this be true for complex matrices? Consider this matrix I, and so if I consider this matrix A, then what should be A star? So A star is so it's I minus I minus I minus I. Let this be 1, 1, right? Now this is surely symmetric. This is symmetric, but it is self-adjoint. Is it self-adjoint, or is it normal? In fact, is it normal? So it's evidently not self-adjoint, right? But is it normal? It's not normal as well. Clear? So real symmetric matrices, we can talk about real symmetric matrices being normal trivially, but it's not true for complex symmetric matrices. Okay. Now I'm giving a brief definition of an important concept of operators, which is the concept of a positive definiteness. I won't indulge much time here. I will just give the definition and I will just give some important properties of it. Okay. So a linear operator T on a finite dimensional inner product space is called positive definite, and respectively there's also a term positive semi-definite if T is self-adjoint, and the inner product of the image of x under T with x is always greater than 0, and if it's positive semi-definite, then this inner product needs to be non-negative. Okay, and this happens for all x in V. I should rather be specifying for all non-zero x, right? For all non-zero x, right? Clear? So a real or complex n cross n matrix, if I talk about, it's positive definite or positive semi-definite if the linear operator induced by it is so. Okay, so n cross n real or symmetric matrix is positive definite or positive semi-definite if the linear operator induced by A is so. Okay, let us talk about some important properties of it. I'll just give 2 or 3 theorem. Let T and U be self-adjoint linear operators on an n-dimensional inner product space V, and let A be the matrix of T with respect to beta, where beta is an orthonormal basis for V, okay. Then number 1, T is positive definite if and only if all its eigenvalues are positive. In fact, I can also talk about it being semi-definite if and only if all its eigenvalues are non-negative. Okay, let's give a quick proof of this first. The proof is fairly easy. Suppose let us say alpha is equals to, say, v1 v2 till vn be an orthonormal basis. Okay, I have chosen to be beta, right? So is an orthonormal be an orthonormal basis for V, such that each Vi is the eigenvector. Now we know about its existence because we are talking about self-adjoint operators, and each Vi is the eigenvector corresponding to eigenvalue lambda I. Okay. Now for all x in V, I can write x as a linear combination of these vectors ai in the form of ai vi. Let's say I is equals to 1 to n. But then what can I say about the inner product of tx with x? So see, what can I talk about tx from here? So it's summation I is equals to 1 to n. Since t is linear, so it's ai times t of vi, but t of vi is lambda I vi, right? So therefore the inner product of tx with x, it is basically the inner product of summation I is equals to 1 to n ai lambda I vi, and here I have summation I is equals to 1 to n ai vi. But observe that if I decompose it out, then since these vi's, let me write use the index j here. Okay, so what will I actually get? So if I decompose this out, the scalar parts come out. So I'll get, typically, since we are talking about an orthonormal basis, So what should I get? Right. So see, this will eventually come out of this form, right? It will be of the form summation I is equals to 1 to n ai lambda I inner product of vi with summation j is equals to 1 to n ai, say aj vj. Okay, so I have here aj vj, let's say, right? So this will be coming out to be of the form summation I is equals to 1 to n. So summation I is equals to 1 to n. And what can I say out from here is that, so this is ai it as it is, I get one more summation, right? So lambda I, so I get here summation j is equals to 1 to n. I get here aj bars, and here I get vi vj, right? Right. But we know that this part will be 0 for all I not equal to j, and it will be equals to 1 if I equals to j. So the whenever j is equals to I, this part will give you just ai bar. So I can write it as summation I is equals to 1 to n. So I get ai bars from here. So ai times ai bar will give you mod of ai squared times lambda, right? Right. Therefore, observe that therefore the LHS is non-negative. So if I prove it for semi-definiteness, it will obviously be proved for definiteness as well. The LHS is non-negative if and only if each lambda I is non-negative for arbitrary AIs, because this part will be non-negative, right? Clear? Okay. Okay. Because see, we are talking about self-adjoint operators. Right? I get you understood what we did here. Okay. Whatever. What more can we say about its properties? I'll only consider some important ones. I don't want to get involved into very deep results. Okay. Mm, let me think of one more. See, this is actually one of the most important observations I'll be talking about. Okay, that's pretty obvious. Okay. But what more can I say? Okay, let's leave at this property only. In the next lecture, or in some after some lectures, if I feel like, I'll be coming back to the concepts of positive definiteness, and I'll discuss some more properties. But at this point, I don't think we need much more observations, because this is one of the most important observations at least at this point. Okay, that if you consider a positive definite matrix, then equivalently I can talk about its eigenvalues being positive, and if I talk about a semi-definite matrix, then I can talk about it being non-negative. Okay. So now what we want to do is that we want to introduce the concepts of unitary and orthogonal operators. Unitary and orthogonal operators. Okay. So let us straight away come to the definition of it. That let T be a linear operator over a finite dimensional inner product space, where V is a finite dimensional inner product space, let's say over a field F. Okay. If the norm of the image of any vector x under T is same as the norm of x, then for all x in V, that is if this happens for all x in V, then T is said to be unitary if the field is complex. If F is C and it's called orthogonal if F is R. So now see, studying this is sort of intuitive, because whenever we study some arbitrary structure, we always try to consider those functions or those mappings which preserve some important properties, right? Like when we study groups, we want to study those operators which preserve the structure of the group, right? Trivially, what we call the isomorphisms, right? When we study topological spaces, we always want to study those operators between two arbitrary topological spaces such that the operator preserves the topological structure of them, or at least it leads to a correspondence between the open sets of those two topological structures, and such functions are what we call the homeomorphisms. So while we are studying mappings under inner product spaces, it should be obvious that we study about operators which preserve something. Now, when we were previously introduced the concepts of linearity, then we had seen that linearity preserves the operations on vector spaces, right? It preserves the addition operation as well as it preserves the scalar multiplication. Okay. So now what we want to do is that we want to preserve the length of a vector under some operator. Okay, and that's why we introduced the concept of unitary and orthogonal operators. Okay. So an obvious example is that if I talk about the rotational or the reflectional operator over R2, and see, both of them are length preserving, that's quite intuitive and that's quite geometrically evident, right? Because what does a rotational operator trivially does? If I talk about a rotational operator, then that trivially just rotates the vector by some angle. It causes no change to its length. It doesn't scale it out or it doesn't diminish it out. It just rotates it. Therefore, there shouldn't be any change in its length. And similarly, if I talk about a reflectional operator, the same thing happens, right? That we just reflect the vector about some line or maybe origin or something of that sort, but we cause no change to its length, right? Therefore, the obvious examples are the rotational and the reflectional operators. So if I talk about examples, the obvious examples are the rotational and reflectional operators over say R2. One more interesting example, which is sort of quite complicated. I won't say it's complicated in terms of the example, but the space itself is quite complicated. So we had not included this example in any previous case, but here it can be explained similar, in a very simple sense. So we do it. Okay. What we typically do is that we consider the space of all continuous complex valued functions. Let H be the collection of all continuous complex valued functions over 0 to 2 pi defined on this interval, and we define inner product with the inner product of f with g is given as 1 over 2 pi integration 0 to 2 pi ft gt bar dt. Okay, clear? Now if I consider a function out from H, that is an element out from H, let H be an element of capital H such that the absolute value of this function is 1 for all x in 0 to 2 pi, obviously. Okay. Let T be a linear operator on H such that T of f is equals to H times f. Okay. We define a linear operator on H in this way. It's clearly a linear operator. Now what can I say about the norm of TF, or let's say square? So it's the norm of HF squared, but that's inner product of HF with HF. But then that typically what should it give? It gives you 1 over 2 pi integration 0 to 2 pi HTFT times HTFT bar dt, right? But then we are talking about functions, multiplication of functions, right? Multiplications of complex continuous complex valued functions. I can surely consider about them being commutative. So see, what we get is basically modulus of HT squared times ft bar dt, but this part is 1, right? So it is 1 over 2 pi integration of 0 to 2 pi mod of ft squared dt, right? Or let me not write it in this way, let me simply write as it is, uh, ft bar dt, but that's just inner product of f with itself. So it's just inner product of f with itself, so it's just the norm of f squared. Since we are talking about a non-negative quantity, so if I just remove the square, this implies that norm of tf is same as norm of f, right? So this is a unitary operator. Clear? For some given h. Clear? Okay. Now we will end this lecture with a set of equivalent statements related to unitary operators, which will help us characterize it better. Okay. In the next lecture, we will talk about what is called orthogonal equivalence of matrices, or similarly in operators. So theorem, let T be a linear operator on V, where V is a finite dimensional inner product space. Okay, one thing I forgot to mention, let me just quickly mention it out here, that I can also talk about such length preserving linear operators in case of infinite dimensional inner product spaces as well. The problem is that in case of infinite dimensional inner product spaces, the length preserving operators are necessarily, they are necessarily injective, but they are not surjective. Okay, if they are surjective, if length preserving linear operators over infinite dimensional inner product spaces are surjective as well, then we just say them to be unitary or respectively orthogonal. Okay, we use the same terms. Yeah, so let T be a linear operator over a finite dimensional inner product space, then the following are equivalent. Then the following are equivalent. Number 1, T star T is I. Number 2, T star is I. Number 3, the inner product of Tx with Ty is same as the inner product of x with y. That is all. It is also preserving the inner product as well. Number 2, if beta is an orthonormal basis for V, then T of beta is also orthonormal basis for V. Is also orthonormal basis for V. So okay, this is 4, right? This is 4. Number 5 is that there exists an orthonormal basis. There exists an orthonormal basis for V such that 4 happens. Now this statement is quite trivial, so there's no need to prove it actually, because see, 4 immediately implies 5, right? Because we know that since we are talking about a finite dimension inner product space, we can always talk about orthonormal basis for V. And if we consider 4 to be true, that is there exists an orthonormal basis, then just proving 4 simply proves 5. Okay, so there's nothing too complicated in proving 5. Actually that needs no specific proof. Number 6 is that it preserves length for all x. Okay, to prove this, we just simply need one lemma. The lemma is that let U be a self-adjoint operator on an inner product space V, and suppose, okay, let me not use it as a lemma, let me just take this as an observation. Okay, that's not as important even to consider it to be a lemma. And suppose the inner product of x with ux is 0 for all x in V. Then what can I say about this linear operator? Observe that if it is 0 for all x in V, then I can write that 0 is equal to the inner product of x plus ux with u of x plus ux, right? So these parts are same, right? So it satisfies what we started with. But I can write this as the inner product of x plus ux with ux plus u squared x. But then I can distribute it out to write it as x ux plus x u squared x plus ux ux plus ux u squared x, right? Right. But now observe that this is 0 because that is physically given, and this term is nothing but ux u of ux. So this is also 0, right? So this part is 0 and this part is also 0. So we are just left with x with u squared x plus inner product of ux with ux, right? But then observe that I can write this as the inner product of u star x ux, but then u is self adjoint, so it's simply ux. But then I have 2 ux ux, right? So it's 2 times this, so it's basically 2 times the norm of ux squared, right? But if 2 times the norm of ux squared is equals to 0, then that typically implies that the norm of ux is equals to 0, but that happens for all x. That simply means that ux is 0 for all x, which implies u is the 0 operator. Yeah, now let's come to the proof of the statements we have. The proofs are quite simple. There's nothing too complicated in it. So proof number 1. So first we do that 1 implies 2. Okay. See, if t star t is equals to I, then that implies t star t whole star is equals to I star, but I star is I. But then this implies t star is equals to I. So it's a easy statement. How does 2 imply 3? So we have t star is equals to I. Okay. Now I can write the inner product of xy for all x and y in V, where the inner product of xi as the inner product of ix with y, right? I is the identity operator, but I can I write as t star xy, right? Right. So I can write this as inner product of t star x with t star y, right? Or in other words, yeah, I can do this. What more can I say? So see, observe that if I write it, see, if I write it not like this, but in fact, if I write it like this, see, actually 1 and 2 are directly equivalent, right? Right. So in fact, if I write it like t star t x, then I'll get the exact results immediately. So that's it. Clear? How can I say that 3 implies 4? So let beta be v1 till vn be the orthonormal basis. Be the orthonormal basis for v. Okay. So what did I consider? How did I consider the orthonormal? Yeah, I simply consider an orthonormal basis, right? I didn't consider the yeah. Okay. So if beta is the orthonormal basis for v, then consider t beta. We define t beta to be specifically the collection of all elements of the form tv1, tv2, and so on till tvn, right? But then observe that the inner product. So since we have chosen 3 to be true, so the inner product of tvi, tvj is nothing but equal to the inner product of vi, vj. But since beta is an orthonormal set, so it's just delta ij. But that immediately means that t beta is also orthonormal. Now 4 implies 5 is trivial, as I just said previously. It's trivial. How can I say that 5 implies 6? How can I say that 5 implies 6? So what was the sixth statement? Let me just quickly go back. The sixth statement was that, yeah, okay, the norm that t is length preserving. How do I prove that? See, if I consider that there exists an orthonormal basis such that t beta is orthonormal, I mean to say that if I consider a basis, if I consider the existence of an orthonormal basis such that T beta is also an orthonormal basis, then I can consider that basis immediately. So let beta be an orthonormal basis for V, which immediately implies that T beta is also so from 5. Now let beta be given as V1, V2 till Vn. Then for all x in V, I can write x as summation ai vi, I ranging from 1 to n. But then from this implies that the norm of x squared is basically the inner product of summation I is equals to 1 to n ai vi with itself, ai vi, say let's say aj vj. But then clearly observe that since these vi's come from an orthonormal set, or they are mutually orthonormal, this is nothing but summation I is equals to 1 to n mod of ai squared. Just distribute it out. Is equal to mod of ai squared. So let this be statement star. Now consider t of x for all x in V. Then this will be of the form summation I is equals to 1 to n ai t of vi. But then observe that the norm of tx squared is basically the inner product of I is equals to 1 to n ai tvi summation I is equals to 1 to n ai tvi, let's say aj tvj. But then these tvi tvj's are also orthonormal, right? Because t beta is orthonormal, so it will again give us the same result. I is equals to 1 to n mod of ai squared. But you already seen that this equals to norm of x squared, which implies that norm of tx is equals to norm of x for all x, right? Clear? Finally, if I show that 6 implies 1, and that's quite easy, because if for all x in V, I can write the inner product of x with itself as the inner product, or let me say it's norm x square, which is same as norm of tx squared, but this is same as tx x, sorry, tx, right? But then I can write it as the inner product of t star tx x, right? So this implies that this is inner product of I minus t star t of x with x is equals to 0 for all x. But that immediately implies that I must be equals to t star t, right? Okay. So let this lecture be up to this much. In the next lecture, we will talk about some more properties of unitary and orthogonal operators. Meet you guys in the next lecture.